What would happen if we detonated the most powerful nuclear bomb ever created at the deepest point in the ocean? There's a question that lives on the frontier of scientific curiosity and our fascination with destruction. A question that pits the greatest power humanity has ever wielded against the greatest mystery our own planet holds. What would really happen if we took the most powerful nuclear bomb ever built and detonated it in the most inaccessible, deepest, and most alien place on Earth? The answer isn't a simple explosion. It's a cascade of physical events, a battle between forces that defy our imagination. And to understand it, we first need to meet the titans of this story. First, the weapon. We're not talking about just any bomb. We're talking about the AN-602, better known by its nickname, the TSAR Bomba. Built by the Soviet Union in 1961, it wasn't just a weapon, it was a statement. At 8 meters, about 26 feet long, and weighing 27 metric tons, nearly 60,000 pounds, it was a monster. Its test unleashed 50 megatons of energy. But what does 50 megatons even mean? It means a force equivalent to 50 million tons of TNT. That's more energy than all the munitions used by every army during the entire Second World War, concentrated into a single point in a fraction of a second. The shockwave from its test circled the Earth not once, not twice, but 3 times. That's the force we intend to bring to the depths. Now for our stage, the Mariana Trench, and at its heart, the Challenger Deep. A chasm nearly 11 kilometers, or about 7 miles, below the ocean's surface. A depth so great that if you could place Mount Everest inside, its peak would still be covered by more than 2 kilometers, over a mile, of water. But the crucial factor isn't the depth, it's the pressure. For every 10 meters, 33 feet, you descend into the ocean, the pressure increases by 1 atmosphere. In the Challenger Deep, the pressure is nearly 1,100 atmospheres. That's over 1,100 times the pressure you're feeling right now. Try to picture it. It's the equivalent of having a 747 jumbo jet sitting on your body, or the force of 8 tons crushing every square inch. It's an environment so extreme that it distorts molecules themselves, and where only the most bizarre life forms, the piezophiles, can survive, adapted to being crushed. We have the unstoppable force, and we have the immovable object. The collision is about to happen. The guiding question is, when these two absolutes meet, which one gives? The moment of detonation. In the first nanosecond, the plutonium in the bomb's core goes critical. A runaway chain reaction unleashes a wave of gamma rays and neutrons, turning the bomb's heart into a plasma with a temperature of 100 million degrees Celsius, hotter than the core of the sun. And here, the first great battle begins. On land, this fireball would expand ferociously, vaporizing everything in its path. But 7 miles down, it meets its first adversary, the wall of water under extreme pressure. The water can't simply boil and turn to steam. The hydrostatic pressure is so immense that it suppresses this phase transition. So, what happens? The energy creates a cavity, a bubble of supercritical water vapor and plasma, fighting to expand against a force pushing back from all sides. This bubble grows violently but is contained, perhaps reaching a kilometer in diameter. Imagine a miniature star being born and dying within the ocean, vaporizing tons of rock from the seabed and turning the surrounding water into a state of matter that doesn't naturally exist on Earth. But the ocean's pressure is relentless. Having expanded to its limit, the bubble loses its internal energy and the external pressure wins. It begins to collapse. And this collapse is as violent as the initial explosion. Water rushes in to fill the vacuum, colliding at the center with such incredible force that it generates a second shockwave. And for a brief moment, can even generate flashes of light, a phenomenon known as sonoluminescence, but on a scale never seen before. This cycle of expansion and collapse might repeat a few times, like a cosmic bell ringing in the deep, each pulse weaker than the last, until the energy dissipates into shockwaves and heat. But what about the surface? What would a sailor on a ship directly overhead see? He'd feel the shockwave traveling up the water column, a violent tremor from below. The ocean surface above ground zero would rise into a dome of superheated water and, for a few minutes, boil violently, unleashing a massive plume of radioactive steam. A hellish but localized sight. This brings us to the most famous question. Would this create a mega tsunami that would wipe out the coasts of Japan or California? The answer, surprisingly, is no. The reason comes down to geometry. Think of it this way. To create a devastating tsunami, you need to lift a gigantic area of water, like pushing up a giant dinner plate from the bottom of a bathtub. That's what an earthquake does when it displaces a fault line hundreds of miles long. The bomb's explosion, on the other hand, is like dropping a small pebble into that same tub. It creates a lot of ripples at the point of impact, but the energy spreads out radially, in all directions, and dissipates with distance. The bomb pushes water, it doesn't lift it in mass. There isn't enough energy, focused in the right way, to move the Pacific Ocean. So, if the immediate risk isn't a tsunami, what's the real danger? The real danger is quieter and far more lasting. It's the legacy of radiation. The explosion would create hundreds of kilograms of highly radioactive fission products, cesium-137, strontium-90, iodine-131. All of this deadly toxicity would be contained within that initial bubble. When it collapsed, this radioactive soup would mix with the water, the vaporized rock, and the seabed sediment. The result would be the creation of the most toxic zone on the planet, a permanent radioactive graveyard. Worse still, the explosion would kick up a cloud of contaminated sediment, a toxic marine snow that would slowly settle, blanketing a vast area of the ocean floor with poison. Deep ocean currents are like slow-motion rivers, taking centuries to complete a single cycle. This contamination wouldn't reach the surface in our lifetime. It would remain down there, a ticking time bomb for the distant future, poisoning abyssal creatures and entering the deep ocean food chain in ways we can barely predict. It would be an act of planetary vandalism, with consequences that would outlast every nation that has ever existed. One last question remains. Could we crack the planet? Could the explosion trigger a cascade of earthquakes or activate the Pacific Ring of Fire? The energy of the TSAR BOMBA, while immense by human standards, is a whisper compared to geological forces. The Earth's crust beneath the Mariana Trench is over 100 kilometers, more than 60 miles thick. The bomb's energy, concentrated in the water, wouldn't have the force to cause any significant fractures. It would be like trying to knock down a skyscraper with a hammer. You might scratch the surface, but the structure remains intact. The explosion would be registered as a major seismic event worldwide, but the idea that it could destabilize tectonic plates is, thankfully, the stuff of science fiction. In the end, this thought experiment leaves us with a profound and humbling conclusion. The clash between man's ultimate power and Earth's ultimate depth reveals that our planet is far more robust and powerful than we imagine. The ocean's pressure and sheer vastness are a natural shield, capable of absorbing and containing even our most extreme fury. But it also reveals a darker truth, that the greatest harm we can cause isn't the loud and explosive kind, but the quiet, the unseen, and the permanent. We wouldn't destroy the world in an instant, but we could poison it for millennia. The real lesson isn't about the power of our technology, but about the wisdom and responsibility to never, under any circumstances, use it this way. The greatest mystery of the Mariana Trench isn't what would happen if we destroyed it, but what we still have left to learn from it.